Okay.
Hello everyone, welcome back. We are on session number 4 for room number 1. Please let me introduce now my lovely panel, Developing and Deploying Machine Learning on Embedded Devices, the Biggest Barriers. So here we have Robin Mitchell, editor at Electropages, who's going to be the moderator for today. And then we have Sinisa Patkovic, co-founder at Yatto. Hao Zheng, co-founder and CEO at Robok. Chris Shaw, director of Endpoint AI ecosystem at ARM. And finally, Adam Taylor, ambassador and embedded systems consultant at Edge Impulse. Thank you.
Brilliant. I might just get a timer out because last time I went over the time. Fantastic. Okay. Right, so this panel is concerned with machine learning on embedded devices, microprocessors, microcontrollers, and the challenges that engineers face when trying to make that a reality. We all know that AI has been one of, I would say, is probably going to be the 21st century's greatest developments next to the transistor. I would say I would say that for sure. And it's been easy to develop from the point of view that we've got lots of data, big computers. And we can process all of that, to the cows come home. But when it comes to embedded devices, we need to try and get ML working on these sort of small edge devices, and trying to go from a very large computer that has all the processing power and energy you can imagine to something that's the size, of a fingertip, presents major challenges. So I'd like to go through each of the panel members here, and basically, in your own words, why you think, or what the biggest challenges are of implementing ML on MPUs and microcontrollers in general. Start with you.
Okay, sure. I think everybody's here at a different level in the edge computing stack. So I think we're a little bit lower in the stack. So my name is Sinisa, and I'm an investor and co-founder of Yatto. So edge computing and the challenges. So we just to explain what we do, so you understand where I'm coming from. So we have built a wireless network specific for edge computing, and we are essentially controlling the hardware directly, unlike many other companies, whereby we put machine learning on our chipset, I must mention that, and control the radio, the chipset, and make machine learning work in a very tiny device. But as we control the whole operating environment, we have a lot of visibility into the issues, and the issues, obviously, many of these devices have to be battery powered, some are solar powered, some are AC powered, and so the issues are, there are no, at least we couldn't find a framework or something to latch on to build our layer on, so we essentially have to go and code directly to take advantages of the ARM architecture as well as the other chipsets we're servicing. So essentially it's physics you have to deal with in terms of how you orchestrate all of that happening and how you make your device super intelligent, because in edge network, it's a real-time network. You cannot have your devices sleeping and waking up on a cycle. You heard of that, right? LoRaWAN, whatnot. In edge network, these devices have to be super intelligent and they have to be responsive, yet they cannot waste battery, which is a tremendous challenge, right? But we have overcome these through some new intellectual property and some patents and so forth. So I'll just say, not to take so much time from others, but we have a lot of lessons in that space, and it's not trivial at this point, I must say.
Right.
Sure. Hi, everybody. My name is Hao. I'm a co-founder and CEO of Robok. Originally, we were a spin-out from University of Cambridge and really focused on building or turning 2D cameras into intelligent 3D sensors with our AI algorithms and focusing for the low-power deployment. What we found in terms of the challenges for deploying, it's really finding the optimal balance and trade-off between the performance from a power perspective, functionality, what really brings value to the customers, because what really value to the customers might be something that's of a higher spec in terms of the performance. They might want to know more than if that's a person, if that's not a person. They might want to know a bit more about the behavior and things that's just a little bit more intelligent and potentially also more computationally expensive. How do you balance everything and also the cost of the hardware and software? So this is a topic very close to our heart, and very happy to be here today to discuss this with everybody.
Thank you. So my name is Chris. I work for ARM, based at the headquarters in Cambridge, and this is the first time I've been out of Cambridge for I don't know, nearly 2 years. You no idea how hard I had to hunt to find business cards this morning because I haven't used them in 2 years. So it's lovely to be here. In terms of biggest barrier to deployment of AI at the endpoint, I think the ecosystem just isn't there yet. There's no small number of well tried and trusted techniques, best practices, components that you can put together to implement a nice end-to-end solution. We've been doing MCUs for 50 years now. We know how to do that. We know how to do the trade-offs between memory and power and performance and size and cost. We know how to do that. We know how to do real-time operating systems. There's a lot of really nice ones out there. They're all well tried and trusted. And we've just about got used to connecting things to Wi-Fi and Bluetooth, and there's a good ecosystem. But to do that now is fairly easy to do. You can pick up parts off the shelf, but ML hasn't got there yet. You can't go and pick up parts off the shelf and drop ML into your endpoint system. And I think until we get to that point, until some of these techniques and components and tools get critical mass in the marketplace, and there is a critical mass of knowledge and capability about how to do this, I think we're going to have problems, and we're going to get people doing really, really nice point solutions. And there's loads of those out there. There's lots of people doing really, really cool stuff, but they're point solutions, and they don't necessarily scale and generalize to what the industry needs to deploy in the trillions.
So they're quite specialized, you'd say? Like the solutions that currently exist are specialized?
There's lots of very specialized solutions, but no real general framework to actually kickstart this revolution that we're all waiting for.
Hi, I'm Adam Taylor, and I'm here today representing Edge Impulse, and we actually are a framework that can help you create machine learning and deploy machine learning at the edge. I've spent the last 22 years now working in embedded system development for FPGAs and for board designs. And I think, I agree with Chris. I think your point is a brilliant point about, we need frameworks that will come across and that everyone can standardize and work on and get experience and work with. But I think, the other members of the panel make good points as well, because we're typically, in the embedded world, we're really working with memory constrained, power constrained, space constrained applications. And we get unique applications as well, like that we don't, unique challenges, I should say, that we don't get when we're not at the edge. So not only do we have to worry about machine learning and the frameworks, but we also have to, and the other constraints, we also have to worry about things like security and protection, and can somebody access it? Can somebody make some changes and trick it and make it do something that we don't really want it to do? So I think as well as the sort of the AI and the deployment of it, we've got that whole system view that we need to take a look at as well and consider that when it comes to the AI solutions at the edge.
So in terms of, because I've got three sort of points listed: energy, computation, silicon space. Of those three, which would you say might be one of the bigger sort of challenges in actually trying to implement some kind of ML system onto a chip, would you say? Start with you.
I agree with what Chris said. There is no low level, so there's nothing that sits on top of the. If you want to make a true embedded device that's also very power efficient, there is no framework for you to tap into to sit on top of the silicon. You have to code it yourself. At least this is our experience. Now, once you get to operate the environment and to run the ML, depending on what's the purpose of the ML, we run ML for the core network. So our network runs on ML, which is interesting, right? So it's not that we piggyback off of some star topology network and then we run ML on top of the OS. This just can't run on battery, right? Just by definition, the battery would be, the size of a car. So how do you run ML on a battery on an embedded ARM? We solve that problem. So that's our sort of secret sauce. But there's no framework. We actually had to go, and as you said, we actually had to go to see an assembler and orchestrate the environment. And so for us, the issue is that there's no framework for embedded. Now, once you get to actually above that, you have data, you extract the data, and then I think this is where you can get some frameworks already, and this is great. But how you're going to actually run on a small embedded device, I believe is, for us, at least from what we've seen, is the biggest trouble at the moment.
So would it be right to say that one of the biggest challenges, I'd say, with running AI on, or ML in general, I suppose it's sort of very similar, AI, ML, sort of very, very similar. So one of the challenges is the fact that you're sort of at the moment you sort of run it on top of the software as like a software package. And what you really want to do is actually have something sort of dedicated in the silicon space that can accelerate its sort of performance in terms of energy as well. So it's not really a one problem. It's multiple problems that we currently face in terms of hardware.
It is a multi-dimensional problem. You say you solve the energy problem for your particular use case. That doesn't solve it for everybody else's use case, unfortunately. And you kind of need this change in mindset, which we've seen happen several times before. From ML up in the cloud, you don't have an energy budget. You can have as much energy as you like. And you don't have a memory budget because you're renting it and you can have as much as you like. And you don't have a compute budget because you've got GPUs falling out of your racks and all over the place. So you don't actually care about any of that stuff. You just max out the performance and you go for it. When you start moving that to the endpoint, yes, energy does become a problem because often you're battery powered. Yes, size and cost and memory do become a problem because most MCUs probably only have 256K of memory, which is not enough to do realistic ML processing in. Processing power, I think, is less of a problem. There's a lot of scalable MCU solutions out there that will give you everything from 100 megahertz to 3 gigahertz these days. So there's lots and lots of performance around. But getting use of that within the constraint of the embedded environment is a mindset challenge that I think a lot of developers have got to come to terms with.
So you would say that in terms of using ML, that the challenge really isn't processor speed, it's more about the data itself. It's about having the memory, the ability to actually process that data fast enough.
I would say it's about making efficient use of the compute resource that you have. And that includes compute, memory, energy, bus bandwidth, all of those things. It's making best use of those. So, people like Edge Impulse doing great work in things like quantizing networks, reducing size of data types from 64-bit to 4-bit and finding it still works, which is amazing. And a lot of that it's making most efficient use you can of the resources that you have. In the cloud, you don't care. Embedded, you really care.
But it still needs to operate within a sort of certain time. And it has to be able to operate at a certain speed. Because you could make it, I imagine you could make it very, very efficient if you made it very, very slow. But
it depends really on your application. So some applications, you want it relatively fast. So if you're monitoring an industrial machine, for example, and it's a motor and it's spinning really fast, you want it to be fairly responsive. Another example I've been working on recently is an agricultural robot which drives along very slowly and takes pictures of crops and identifies them and classifies them. I don't really care how fast. We don't really care how fast that robot moves. What we really care about is the fact that we can take a picture with low energy and within a thing. So the fact it takes us 3 seconds to classify an image, in that case, is fine. If it took us 3 seconds to classify the fact that a motor was vibrating badly and about to break and destroy an expensive plant, then that's a challenge as well. So it really comes down to, as engineers, it always comes down to understanding the requirements you've got and picking the right tool for the right job, and then doing that optimization for it.
So with your application, you talk about the agricultural robots. Are these the ones that they autonomously go through fields and they identify weeds and stuff and then destroy them targetedly, or is it a different type of application?
This is actually a different one. So this is actually a trials robot. So it's actually looking at crops as they're growing through agricultural trials to try and work out whether how it's growing and how it's maturing on its journey to hopefully try and make sure that the plants will be better yielding and such like.
Oh, so you're gathering data, which is training an AI to then gather more data to train another AI, basically, to find out the optimum way to grow a crop.
Pretty much, yeah.
AIception, probably. Brilliant. But I would say that when it comes to sort of running these ML applications, that data is extremely important, and the ability to get to data fast is very important because when you were saying about the fact that microprocessors tend to have about 256 kilobytes, the ones that you're working with in terms of static RAM. So my question would be, what kind of memory requirements do you typically see when trying to put ML onto a microprocessor? What kind of memory sizes are we looking at?
It would definitely not be in the kilobyte because of just the size of the model and everything. So what I also like, an anecdote of a customer that we're working with is they need the camera to be solar powered and there's no power supply at the site. And it would be ideal if the compute device could also run on solar power. So if you think about everything combined together, and there's not really a dedicated hardware, you probably use a development board from one of the semiconductor suppliers. Then everything, it becomes this many loose parts. You put everything together. Then you might then think about, is solar power going to be enough? Then you may then start to make compromises in terms of, okay, maybe that's the camera will just be for data collection purposes, and then you process it offline relatively on maybe an embedded board that could be powered, or you just only wake up the compute platform when you've got interest data, etc. So there's a lot of the compromises from the engineering perspective you need to make it work for the customer. So and I guess for dedicated hardware that's like programmable, for example, like a programmable smart camera that's sufficient to run sophisticated algorithm that could have maybe tens of megabyte or maybe a bit higher than that, or if the device is like that, I guess there's a lot of uses, but then the problem is, does it actually scale a lot? Is there a lot of demand? Is it going to actually attract investment for people to make a hardware? Is it going to sell in large volume? Then I guess we see a lot of like smart cameras, like Ring and etc.
And I suppose it should be emphasized that 10 megabytes of RAM doesn't sound like much, but that's on-chip memory that has to be accessed within maybe tens of nanoseconds. So we're not talking about DDR, like your standard motherboard. You can add an extra slot of RAM. You can have 4 gigs, 8 gigs, 16 gigs. It doesn't matter, but the speed at which you can access that memory is probably more critical. But then that comes back onto your earlier point, because you're saying that if you know how to use your resources efficiently and effectively, then speed wouldn't be a problem if it can be done slowly. So then other cheaper sources of memory could be a viable option in that, depending on the application.
Again, trade-off, speed, and energy consumption. Typically the two things are trading off. The faster you clock a processor, the hotter it runs and the more energy it uses. So if you need that power, well, you've either got to reduce the number of cycles you need or increase the number of joules you use. And I can see you're itching to comment on that one.
Please go for it.
Yeah, so I'll just tell you a story. So you have a customer who says, okay, we need, we have this high value equipment in the edge, and cellular doesn't cut it for this reason, and LoRaWAN doesn't cut it, and nothing cuts it. So we want to run the apps that are real-time apps in the edge. But you see, here in this area, you're going to have some power, but there's like 70 kilometers, and you won't have power everywhere. And we like this to be real-time, and we want to manage real-time. And like, okay, I get the requirements, right? So I call around, and I find a company in Sweden that's putting together a framework, relatively low-level framework for edge that is power-efficient edge. And these guys say, oh, it's no problem. We got it solved for you. You just, put a Linux, and then on Linux you put, Java and web and this and that. And I'm like, where I'm going to run this on battery that has to be there for 5 years? Linux with also, it just doesn't, it's a non-starter. So what we had to do, because there is no OS that can satisfy this use case, we have to craft our own state engine. I don't call it OS, I call it a state engine. That's machine learning based state engine, highly optimized for ARM, that actually can deal with this, that can make the device not use power, but be immediately available and immediately learn and understand as the packet comes. Is it packet for me? Do I have to learn from it? Or is it to go somewhere else? And not waste any cycles. That was, I honestly must say, very complicated. And for some reason, I believe that, edge on embedded is a completely different beast, and it's going to have a different set of technologies than embedded or sort of mainstream computing platforms. That at least that's been our experience over the last few years.
So moving on, there seems to be a drive to try and add technology in every aspect of life. You look at the average home now. You can buy IoT toasters and kettles, and you sit there. Yeah, exactly. You sit there and you think to yourself, what's the bloody point? If I'm going to go boil a kettle, just walk across the room, fill it up, and put it on. So there's an obsession of trying to integrate technology for the sake of integrating technology. Now, the reason why I'm saying this is because we might have in the future we'll have the capability to put AI and machine learning algorithms onto microprocessors, but that just might encourage people to add it or integrate it into applications that don't need it, which could leave users exposed. So my question really is that, do you feel like that this might see things like regulation being introduced in the future? Because they've already got regulation for things like, what's the one they just did recently? The one with the, the government just did it about the default passwords and the security. So they're already starting to legislate what we can even design. So I'd like to bring it to you first, if that's okay.
Yeah, of course we can. Yeah, I do think that we have some interesting challenges coming up around AI and the ethics and how we use it and what it's deployed in. And there's also, do you know the most dangerous word in engineering? Is it's interesting. When an engineer tells you it's interesting, he's going to find a reason to use it, whether there's a justified reason or not. And he's going to do, and I've used it in the past. Oh, it interests me, so I'll put it in there. And you're going to see a lot of that because there's a lot of buzz around AI as well. So people are, we should use it, we should put it in our products. We don't know what we're going to do with it, but we should definitely have something in there and we can tick some marketing buzzwords. So I think you're going to find a lot of people trying to find very interesting use cases, and in a lot of cases I think it'll be a solution without a problem that people will need to look at. But it's like everything. I think we're on a journey. People are learning what you can do with it, what you can't do with it, and where we go. But I think you will see more. I think you will see a lot more machine learning deployed in very sensible ways, actually, in a lot more sensible ways than you will see in people sort of doing stupid things with it. And I think there's a lot of use cases where it's really powerful and it can add a lot of value. But I'm not sure I need it in my toaster to tell me whether the toast's at the right thing, this is the thing. My milk to tell me whether the milk's gone off.
Well, this is the thing, isn't it? I mean, you say like, there's going to be a lot of use cases where it's good and a few where it's bad, and it may not be as bad as you think. But I think you take a look at, for example, IoT. I think last time I checked, it was 21 billion devices worldwide, and that was before regulation was put in. So that leaves you with billions and billions of devices around the world exposed, leaving people potentially open to attacks, private data being stolen, en masse in scales that can't even be conceived by the mind. So I think what I'm saying is it going to take 20 years for all these things to be developed? You've got systems that can learn from you, that can also record your private data, store them somewhere like the Amazon Echo. It's sticking all your conversations on the server, which you don't. So, give you an example, you could shout your Wi-Fi password across the room to one of your friends, but the Amazon Echo will pick that up and probably store it somewhere at some point. And so now your password's on a server which is outside of your control. So my worry is that by encouraging this use of AI onto microprocessors, will we see it be used too much before it's too late? Before we sort of draw the line in the sand and say, look, we've got to be ethical about this implementation.
So I'm just going to quickly answer that and then let somebody else talk. But if you think about it, like your Amazon Echo, it's got real world sensors on it. It's got microphones. It's got things that can pick up on it. I think you'll see a lot more of the edge devices don't have necessarily microphones. They might have accelerometers, pressure sensors, temperature sensors, but they'll not have as sort of the human type interfaces that you might have. I'm not saying that you can't do damage with it and people won't do silly things because we're humans and we will and we never seem to learn. Eventually we learn, but we never. But then this is where
it gets interesting, because then if you have a system that can record, for example, voltage off, let's say, across a capacitor, I think some capacitors can actually be used as microphones. And so this then becomes a problem where suddenly you can turn a voltage sort of reading port from a microcontroller to read a capacitor, which is acting as a microphone, and suddenly you've got audio data. So it's one of those things where it's kind of like you'd be amazed what people can do. You'd be shocked what they can do.
And it comes back to what I was talking about earlier on with not only do you need a regulatory framework, but you need people doing the designs and understanding the requirements and the systems and how it's actually going to work and doing that system integration to prevent some of this stuff. You could do differential power analysis and pull keys out and store things if you can monitor temperature, monitor voltages. So there's a lot of things you could do. Whether people will or not, my biggest concern with AI actually is what the government uses it for.
I couldn't agree more.
If I'm completely honest, I'm not worried about what some developer does in his bedroom for a bit of fun or whatever. I'm absolutely terrified about what governments are going to do with it.
I think there are 2 or 3 ways that the world gets rid of bad ideas. And we're quite good at getting rid of bad ideas. Either the market decides, no, that's silly. The toaster is a perfect example of that. People might buy it.
Still sells, apparently.
Eventually, it will die out because it's just a silly idea. And then there are bad ideas that probably governments need to step in and say, no, that's not a good use. And you are seeing a lot of, creeping use of facial recognition, for instance. That's the kind of usage which, authorities are going to have to get together and say, well, actually, no, we don't want you to do that. Or if you do, then you're going to have to abide by these privacy rules, security rules, safety rules, and so on.
It's funny you mention AI and facial recognition, because I'm not sure how many people in this room are aware, but anyone here who's got Facebook or social media who's got their photo online, there's a company called Clearview AI, and they've just been recently fined by the UK government, because what they've done is they've gone through all the public records online, taken everybody's faces, the links of where they got those faces, their names and details, they've put them into a database, and they sell that to law enforcement. So when they want to find someone by facial recognition, you're now technically on a police database, and you weren't even asked, and you were never arrested, you were never trialed, and they've got your data, which they're selling your data to other organizations powered by AI. And so,
Here we are spending 5 years putting AI on the ML.
Yeah. I know.
They don't need funding, right? They're bootstrapping.
Because this is why it goes back to government. You can never trust government, can you? But any comments on the ethics?
Definitely. I think what Chris was saying about some consumer products with the AI capabilities is it going to be a very successful product? And if it doesn't justify the price point, etc., these things will discontinue at some point. So that's why we see a lot of these AI being used for like industrial IoT space, where it's probably okay to have all this data being recorded out of the machines and all the devices you're using, because that helps with if it's a throughput business, it helps with productivity, and comes back to the edge. Limitation side. You see a lot of the telco providers that they actually comes with solutions about where is the edge, right? Is it the edge to the cloud, or is it the edge to the sensor or anything? So if it comes to the edge to the cloud, you actually see them using very powerful devices that's actually going to connect to hundreds and hundreds of connection points. So I guess then again, where it's being used is really important. And there are use cases where it's extremely helpful and it does contribute to the economy in a positive way. But as the use case you talk about, there's some rules and legislations about data anonymization and how do you treat them. I think those are really key to control that, because it's always double-edged sword.
I think it's funny you say it, because I think one of the biggest problems as well with things like trying to regulate things like AI and stuff and limit its use is that if you don't do it, someone else will. And so not only will you lose the battle, they will then be on the better side of that. So you look at there's lots of nations around the world right now who are already using AI for cyber attacks. So the only reason why we need to be we need to develop our own AI to make sure that ours can beat theirs. And if we don't, we immediately lose in a year or two. So I think that was I think we should wrap up the conversation and bring it to questions from the audience. Do we have any questions for our panel members? Well, we're on right there. Can we get a microphone to them, please? Thank you. Just chuck it across the room. I have absolutely no idea.
In your opinion, means where we can use means what technique of machine learning we use, especially in wireless network, means either we need to use the supervised learning technique or unsupervised, or means which technique usually used in dealing when we are managing the wireless network or the IoT networks. So which AI technique or machine learning technique is more suitable for that case?
That would be a technical question. Who wants to answer that one?
I hear it actually.
I can give some.
I think you're referring to maybe running on the wireless network. I think I have some answers on, like, in general, the techniques you use, but...
Bring it closer.
Yeah, so just tell you our experience. So I cannot tell you what you should do, right, obviously. So we see edge computing as an enormous opportunity, and we see it in a puristic way. So we don't see it as a half edge or half cloud, half edge or fog edge, whatever. We are developing the platform that actually can be true edge going 20 years from now. And in the true edge, you have to have unsupervised learning happening. In a way, what we're working on, you can think it is freeing AI from the vertical stacking in a data center, which the head of Google AI spoke about, and there are papers about it. So we're saying, okay, forget about vertical stacking of AI in the cloud. To do edge computing properly and to actually have real benefit use cases, apps, whatnot, you have to have that AI becoming distributed AI. And then you have to have that brain happening in the edge, meaning the data centers in the edge, as much as you can. Obviously, it will take time and it will be layers of things. But this will open up the whole array of new opportunities. So we have already built that it has to happen in an unsupervised way. But just to give you an idea, maybe around how this is complicated in an embedded world of today. So we actually have to, in the going all the way down to talking about artificial neural network, how it works. We had to actually enable it to virtualize itself, to span itself virtually into nodes around itself, because it cannot, in some of the nodes that have to learn more, and I call network endpoints as nodes, right? One can overgrow itself and it has to span itself around, right? That's what we're talking. So it's in a way a form of parallel computing, a form of distributed database, and all of these things will have to be developed. It's just that we decided to start this relatively early, so we're hacking through it and developing and solving all these problems ourselves. But over time, there's going to be frameworks and apps and so forth. But the use cases are tremendous. So you're going to have your street lights learn the behavior and communicate that immediately to the traffic lights. It will not have to go to any SCADA or any whatever. This is the edge. You're going to have your ambulance and your street lights and your traffic lights talk in real time as the ambulance goes. That's the edge. And the street lights will optimize the route and flash before the ambulance comes, and the traffic lights will orchestrate with street lights and the ambulance in real time. That's the edge. So that's what we are building towards, right? So you take cloud out of these equations completely, right? As much as you can.
Right. Any more questions? I think we had this one over here, please. There's nothing on. Hello?
Hi. So I have very a naive question, which is related to the first part of the discussion. And let's say on one extreme that the most efficient implementation of ML is going to be a hardware, right? We just build kind of a neural network, let's say.
Get closer, thank you.
Yeah, we just build a neural network on the hardware, right? And of course, this is highly not flexible. I mean, very difficult to do, kind of, right? Unless we find a way of, 3D print neural networks, right? On other extreme, we have this a structure basically of a computer, which is, let's call it, a Neumann or Turing, right? With the processors and memory. And it's highly inefficient, right? So my question is that, can it ever be a middle ground? Can we have a middle ground, right?
That's what we want as well.
Yeah, I think the idea of a flexible platform that can occupy the middle ground and occupy ground on either side of that is a good idea. FPGA is a good example.
FPGA, yeah.
One question. Yeah. Sorry, he was first.
Thank you. I got a couple of questions actually, but I'll try and keep them.
We'll have to keep the questions quite quick, because we're already over by 5 minutes.
Sure. Okay. Okay. In terms of the market segments, do you see? I went to Medica a couple of weeks ago and talked about AI, and they were like, "Oh, some people just like, no, 20 years before that you see that in the medical industry or anything like it because of regulatory type stuff." But then my friend here was talking about agriculture, and that's public and nowhere near agriculture normally. So maybe that's the best place. Where do you see AI? Which market vertical do you see as perhaps pioneering it or leading the way? And then secondly, for products being designed today with NPU engines on board already, like IMX8 M+, that already has that hardware on board, is it easy to retrofit? So a customer designing in with a chip like that, no plans as yet or doesn't know how they're going to use AI, but that chip's going to be around for 15 years and they may want to be able to upgrade their software in order to actually implement it. And what you were saying earlier on about it being part of the operating system, so it's a complete rebuild and how that's going to be, complete visualization. Sorry, lots of questions, but please give me the onions.
Choose the best one.
Well, can it be which industry, and can it be retrofitted? That's two. I got to have both. Sorry.
So I'll take a quick shot at that and then I'll pass it on. I mean, in terms of industry, it's varied. My experience is in the sort of the industrial elements. So so in monitoring machines, the agricultural ones, some work around aircraft and drones as well, but nothing sort of that would sit on the safety critical path, for example. I think you'll see AI moving pretty quickly actually into other areas as well, into medical and stuff. Maybe not initially in products, but certainly I know of research projects that are using it to detect arterial fibrillations, for example, via like your smartwatch, so that you can, if it happens to occur to you, if you're subject to it, it can trigger warnings and take things in. So that's a fairly easy, low impact way to get people used to AI in the medical. Sorry. Into embedded devices, yeah, it's in like a little it's like a smartwatch type thing, but it's an embedded device. In terms of flexibility, I'm an FPGA engineer, so I'm going to say, if you want that flexibility, redesign it in. FPGAs are brilliant for that, but actually, processors are generally pretty good as well. If you look at the ARM processor, they've got the Neon engines and such like, which enable vectorization, so they can be used. And I'm sure Chris knows an awful lot more about what specifics they might have put in them for doing that. Upgrades and that future product roadmaps, I guess, is the word to use. Last point?
Yeah.
Last point, yeah. Okay, Nico.
I'll be quick. So first in medical, I think there's a lot of AI being used for medical imaging, so that's one way. Obviously there's also robotics, etc. In terms of retrofit, I guess AI could give you a lot of information that maybe to aid people to make decisions. So if you basically you could put additional embedded platform into a bus, then all of a sudden your bus cameras become smarter because it helps you to detect vulnerable road users in a blind spot, etc. And the last question about updates, I guess. If you look at Tesla's full self-driving computers, being software upgrades to improve the functionality as the system gets smarter with more data collected, and also there's a lot of work in digital twin where it's really a software and hardware code development. So there's a lot of things you could simulate pre-silicon. So you can actually have the software engineers start developing for the hardware that's not yet manufactured. So there's a lot of vendors doing that. So that might be a way of really designing a really fit-for-purpose hardware system for highly complex and safety-critical systems.
Fantastic. Is this on? It is working, isn't it? Yeah, brilliant. Yeah, right. So I think that's all the time we have. We've gone over by about 5. Oh, he's really got a question. You'll have to ask it afterwards because we've got other people coming through. So come up afterwards and that'll be great. But other than that, thank you ever so much for being here. Please give a round of applause to my fellow panel members, and thank you very much.